Maxima and minima. Stationary points. Stationary points on a graph are points where the gradient is 0. On a graph y equals function of x, the stationary points have dy by dx equal to 0, and there are three types of stationary points. We can see these in the diagrams. In the first we've got a local maximum, in the second we've got a point of inflection, and in the third we've got a local minimum. Now the first is called a local maximum because it's the highest point on the graph for all points nearby. There may be higher points if we look further along the graph. Similarly, a local minimum is the lowest point in a nearby region. Let's consider turning points. Local maxima and local minima are called turning points because the gradient of the curve changes sign on opposite sides of the point. So in a local maximum, on the left-hand side the gradient is positive, and on the right-hand side the gradient is negative. So the gradient has changed sign. An inflection point is not a turning point. In the above diagram, the gradient is positive on either side of the stationary point. The sign does not change. Note, a point of inflection does not have to be a stationary point. In the diagram here, the direction of the curve changes at the point, but the point does not have gradient 0. However, when considering points of inflection, we will only consider stationary points. Let's look at an example. Example 1. Given that y equals x cubed minus 3x squared plus 1, find the stationary points. Determine if each stationary point is a maximum or a minimum. In part 1 we have y equals x cubed minus 3x squared plus 1. So when we differentiate we get dy by dx is equal to 3x squared minus 2 times 3x to the power 1 plus 0. So dy by dx is 3x squared minus 6x. Now, to find the stationary points, we let dy by dx equal 0. So we have 3x squared minus 6x equals 0, and we can divide all the way through by 3. X squared minus 2x equals 0, and that factorizes as x into x minus 2 equals 0. Now, if two things multiply together to make 0, one of them is 0, so x equals 0, or x minus 2 is equal to 0. So x is 0 or x equals 2. If x is 0, in the original equation y equals x cubed minus 3x squared plus 1 means y is 1. And if x is 2, then y is 2 cubed minus 3 times 2 squared plus 1, which is 8 minus 12 plus 1, which is minus 3. So the stationary points are 0, 1 and 2 minus 3. Now in part 2 we want to determine if each stationary point is a maximum or a minimum. Well, to find the nature of the stationary points there are several methods we can use. The first method, if we choose a point on either side of the stationary point and evaluate y, we can spot what type of stationary point it is. So for 0, 1, if we take x is equal to minus 0.1, y is equal to minus 0.1 cubed minus 3 times minus 0.1 squared plus 1, and that works out to be 0.969. At x equals plus 0.1, y is equal to 0.1 cubed minus 3 times 0.1 squared plus 1, which is equal to 0.971. So if we look to see what the value of y is at the three values, x is minus 0.1, x is 0, and x is 0.1, we see the highest value is the middle value when x is 0. So 0, 1 is a maximum. If we look at the point 2 minus 3 and take a point on either side, let's say x is 1.9, we get y is 1.9 cubed minus 3 times 1.9 squared plus 1, which works out to be minus 2.971. At x equals 2.1, y is 2.1 cubed minus 3 times 2.1 squared plus 1, which works out to be minus 2.969. And so we see the value minus 3 is the lowest value, and so the point 2 minus 3 is a minimum. If we look at the first example and look at the second part again, determine if each stationary point is a maximum or a minimum, we can choose a point on either side of the stationary point and evaluate dy by dx to see the type of stationary point. So, for 0, 1, at x equals minus 0.1, we have dy by dx is equal to 3 times minus 0.1 squared minus 6 times minus 0.1, which is equal to 0.63. At x is equal to 0.1, dy by dx is 3 times 0.1 squared minus 6 times 0.1, which is minus 0.57. So, to the left of the stationary point, the gradient is positive, and to the right of the stationary point, the gradient is negative. So the gradient changes from positive to 0 to negative. This shows us that we've got a maximum. So we see 0, 1 is a maximum. Now for the point 2 minus 3, at x is equal to 1.9, dy by dx is equal to 3 times 1.9 squared minus 6 times 1.9, which is equal to minus 0.57. And at x equals 2.1, dy by dx is equal to 3 times 2.1 squared minus 6 times 2.1, which is equal to 0.63. So on the left the gradient is negative, and on the right the gradient is positive. So the gradient changes from negative to 0 to positive, which shows that the point 2 minus 3 is a minimum. Now there is a third method using what's called the second differential. If we consider a graph of y equals function of x, and underneath draw the gradient function, dy by dx is equal to function dash x. For the graph y equals function of x, at a and b the gradient is 0, so the gradient function lies on the x-axis. For x less than a, the gradient is positive, so the gradient function lies above the x-axis. And for x lying between a and b, the gradient function is negative. And for x greater than b, the gradient function is positive. We notice at the maximum point a, the gradient of the gradient function is negative or 0. We notice at the minimum point b, the gradient of the gradient function is positive, or possibly 0. So, for y equals function of x, dy by dx, which is f dashed x, is the gradient function. If we differentiate dy by dx, so that's dy by dx over dx, we call that f dash dash x, that's the gradient of the gradient function. Now for short we write that as d2y over dx squared. At a point P, if d2y by dx squared is less than 0, we have a maximum. At P, if d2y by dx squared is greater than 0, then we have a minimum. At P, if d2y by dx squared is equal to 0, then we do not know the nature of the stationary point. So, if we return to example 1, in part 2 we want to determine if each stationary point is a maximum or a minimum. Well, we have dy by dx equals 3x squared minus 6x. So if we differentiate again, we have d2y by dx squared equals 2 times 3x to the 1 minus 6. In other words, 6x minus 6. Now if x is 0, then d2y by dx squared is equal to minus 6, and negative means it's a maximum, so 0, 1 is a maximum. If x is equal to 2, then d2y by dx squared is equal to 6 times 2 minus 6, which is 12 minus 6, which is 6, and positive means a minimum. So 2 minus 3 is a minimum. Let's look at another example, example 2. Given that y equals x cubed minus 9x squared plus 15x plus 9, find dy by dx. Well, we have y equals x cubed minus 9x squared plus 15x plus 9. So dy by dx is 3 times x squared minus 2 times 9x to the 1 plus 15 minus 0. So dy by dx is 3x squared minus 18x plus 15. Now in part 2 it asks us to find the stationary points. Well, let dy by dx equal 0. So 3x squared minus 18x plus 15 equals 0. We can divide all the way through by 3. So x squared minus 6x plus 5 equals 0. And we can factorise that. It factorises as x minus 1 into x minus 5 equals 0. Now if two things multiply to make 0, one of them must be 0. So x minus 1 is 0 or x minus 5 is 0. In other words, x is equal to 1 or x is equal to 5. Now if x is equal to 1, y is equal to 1 cubed minus 9 times 1 squared plus 15 times 1 plus 9, which works out to be 16. And if x is equal to 5, then y is 5 cubed minus 9 times 5 squared plus 15 times 5 plus 9, which is equal to minus 16. So we have stationary points at 1, 16 and 5 minus 16. Now in part 3 we're asked to classify the stationary points. Well, we can do this by taking the second differential. So dy by dx is equal to 3x squared minus 18x plus 15, and when we differentiate that we get d2y by dx squared is 6x minus 18. Now if x is equal to 1, then d2y by dx squared is 6 minus 18, which is minus 12, and minus means a maximum. If x is 5, then d2y by dx squared is 6 times 5 minus 18, which is 30 minus 18 or 12, and positive means a minimum. So 1/16 is a maximum point, and 5 minus 16 is a minimum point. Now in part 4, we're asked to sketch the graph. So let's draw some axes. Now it crosses the y-axis at 9. It has a maximum point at 1/16. It has a minimum point at 5 minus 16. And so we can join that with a smooth curve. And that's our sketch of the graph. Let's have a look at another example, example 3. Given y equals x cubed plus kx squared plus 24x minus 17, where k is a fixed constant, we're told there is a stationary point P at x equals 2. Find the value of k. Well, we have y equals x cubed plus kx squared plus 24x minus 17. So dy by dx is equal to 3x squared plus 2 times kx to the power 1 plus 24. So dy by dx simplifies to 3x squared plus 2kx plus 24. Now we know that there's a stationary point when x is 2, so when x is 2, dy by dx is 0. So 3 times 2 squared plus 2k times 2 plus 24 equals 0. Or 12 plus 4k plus 24 equals 0. So 4k plus 36 is equal to 0. Or 4k equals minus 36, which means k is equal to minus 9. In part 2, we have to find the coordinates of P. Now y is equal to x cubed minus 9x squared plus 24x minus 17, and we know x is equal to 2. So y is equal to 2 cubed minus 9 times 2 squared plus 24 times 2 minus 17. So that's 8 minus 36 plus 48 minus 17, which means y is equal to 3. So the coordinates of P are 2, 3. In question 3, we're asked to find the coordinates of the other stationary point, Q. Now, dy by dx is equal to 3x squared minus 18x plus 24. So let 3x squared minus 18x plus 24 equals 0. In other words, x squared minus 6x plus 8 is equal to 0. Now that factorizes as x minus 2 times x minus 4 equals 0. So x is 2 or x is 4. Now we've already considered the case when x is 2. So if x is 4, y is equal to 4 cubed minus 9 times 4 squared plus 24 times 4 minus 17. And that means y is equal to minus 1. So the other stationary point Q is at 5 minus 1. Then it says determine the nature of each turning point. Well, we've got dy by dx equals 3x squared minus 18x plus 24. So differentiating again, d2y by dx squared is equal to 6x minus 18. Now if x is 2, d2y by dx squared is 12 minus 18, which is minus 6, which means a maximum. If x is 4, d2y by dx squared is equal to 24 minus 18, which is equal to 6. And so, being positive, it's a minimum. So, the point P, 2, 3 is a maximum, and the point Q, 4 minus 1, is a minimum. Now to sketch the graph, we can draw out some axes. We've got a maximum point at 2, 3, and we've got a minimum point at 4 minus 1, so we can sketch the graph. Let's look at example 4. This is a practical example. A tray is to be made from a piece of card 40 centimeters by 25 centimeters. Equal squares are to be cut from each of the corners, and the tabs are then folded up to make the tray. What is the maximum volume we can make the open tray? Well, to solve this, let the side length of each cutaway square be x centimeters. Now we can see that the base of the tray will be 40 minus 2x centimeters long and 25 minus 2x centimeters wide. Let the volume of the tray be y. The tray is a cuboid, so y is equal to the length times the width times the height, which is 40 minus 2x times 25 minus 2x times x. That's 1000 minus 130x plus 4x squared, all times x, or y is equal to 4x cubed minus 130x squared plus 1000x. So for a maximum, we want dy by dx to equal 0. Now y is equal to 4x cubed minus 130x squared plus 1000x. So dy by dx is 3 times 4x squared minus 2 times 130x to the power 1 plus 1000, or dy by dx is 12x squared minus 260x plus 1000. So if we want dy by dx equal to 0 to find the maximum, we have 12x squared minus 260x plus 1000 is equal to 0. Now we can divide all the way through by 4. 3x squared minus 65x plus 250 equals 0. Now we can split the middle term up as minus 15x minus 50x. So that's 3x squared minus 15x minus 50x plus 250 equals 0. The first pair factorizes as 3x into x minus 5, and the second pair minus 50 into x minus 5 equals 0. So it all factorizes as 3x minus 50 times x minus 5 is equal to 0. Now that means x is equal to 16 2/3 or x equals 5. But 16 2/3 is impossible. There is not that much cardboard. The width of the cardboard is only a maximum of 24, so you can't cut two squares of over 16 centimetres. Now that means x can only equal 5, in which case the volume is equal to 40 minus 2 times 5 times 25 minus 2 times 5 times 5, which is 30 times 15 times 5, which is 2,250 cubic centimetres. But we should check to see that is a maximum. So if we let x equal 4.9, we get y is 40 minus 9.8 times 25 minus 9.8 times 4.9, which is 2249.296, which is smaller. If we let x equal 5.1, we have y equals 40 minus 10.2 times 25 minus 10.2 times 5.1, which is 2249.304, which again is smaller. And so the maximum is 2250. So we have a maximum volume of 2,250 cubic centimetres. That is when x is 5 centimetres.